when the data is given, there is a different way of calculating. Otherwise, when the joint distribution or joint density function is given, then you have to carry out the various steps which I have already explained you by means of the example. Now, one of the very important joint distribution is known as the bivariate normal distribution. So in short, we call B and B. B stand for bivariate, normal, and variate. Okay. So uh, let us see what is the motivation for studying this particular distribution. And as usual, we are not going to uh, discuss the detailed derivation of this distribution. So we'll focus mainly on its application, and let us see that how to get the uh, marginal densities, conditional density, and make use of that. So if you consider the two class tests, say class test 1 and class test 2. So X and Y indicates the marks obtained in the class test 1, and Y indicates the marks obtained in class test 2. And suppose this distribution of the marks in class test 1, which is represented by X, follows the normal distribution, and it has a mean 75 and variance 25. Similarly, class test 2, Y, which is normally distributed, mean 83 and 16. And then we specify the correlation coefficient between these two class tests. Uh, if you observe in real life situation also, if the student is studying regularly, and if he has done well in the class test 1, then it's more likely that he will do, uh, if not bad, better than class test 1, in the sense that he has got the feedback, and so he will try to improve, and so he may do better in class test 2. And these are correlated. Okay, so it is a consistent way of measuring in that somebody is good, then performing well in the various class tests. He would like, he chances are there he would be performing well in. So there is a positive correlation between the marks. So which is represented by 0.8, and X and Y indicates the as I indicated you that uh, these represent the variable under consideration. Okay, so here variable under consideration is X and Y, so rho XY. If it is Y and Z, then we can write Y and Z. So question is that if a student receives 80 marks in the class test 1, okay, what is the probability that he will do better in class test 2? So this is the information which is available to us. On the basis of that, we have to find out the requisite probability that the student who is going to appear in the class test 2 will be doing better in class test 2, and knowing that he has scored 80 marks in the class test 1. So if we want to write this particular statement uh, in our terminology of the probability, then if you see Y represent the second class test, so Y should be greater than 80, because here the question is that he will do better in class test 2, given that he has scored 80 in class test 1. So given that, we have put here, which is conditioned, and then we are trying to find out what is the probability that he will do better in class test 2. So better means he must score greater than 80 marks. So this is how it is. So it is a conditional probability. So this is the required probability which we need to evaluate. So the usual procedure is that since it is a continuous distribution, so we integrate from 80 to 100. And if we have the conditional density of uh, y given x, then we can find out the required probability. But we do not have information about this conditional density. So the conditional density can be obtained if we know the joint density and the marginal. So I gave you this result that conditional density of y given is x is fxy and divided by the marginal of x. So if fxy is known and the marginal of x is known, then we can get the fyx, that is the conditional density, and if we know the conditional density, I can calculate this required probability. So in order to find the connect, we must know the joint density function of x and y. So what is the joint density function of x and y? So basically the joint density function of x and y, when x is normal, y is normal, and there is a correlation uh, between these two variables which is known, then that particular density we call it bivariate normal. So usually this is a shortcut notation, just like in the case of the univariate normal distribution, we represent x follows the normal mu sigma square. So here uh, the variables are under consideration are x and y. So x comma y, these are the random variable we put in the bracket, and then this is the notation for follows, that x and y follows, and vvn indicates the bivariate normal, and there are 5 parameters. So 5 parameters: mu1, mu2. Mu1 is the mean of x, mu2 is the, here I have explained you, mean of the random variable x, mean of the random variable y, which is mu2, variance of the random variable x sigma 1 square, variance of y equal to sigma 2 square, and rho measures the correlation coefficient between x and y. So the bivariate normal density function, joint density function, is prescribed by 5 parameters, and this is the form of the joint density function. Now, as you will find that it is a very lengthy expression and difficult to remember also, but uh, uh, with little concept, a little help of the uh, x and y, knowing that x and y are normally distributed, so you are multiplying basically the root 2 pi sigma 1 root 2 pi sigma 2, so it becomes 2 pi sigma 1 sigma 2, and this is an extra factor 1 minus rho square square root of 1 minus rho square. Then exponential power is there in the case of the univariate normal also. So here we are dealing with the two normals. So x minus mu1 by sigma 1 square, and then you write plus y minus mu2, this and this. Then the product of these two. So product of these two means x minus mu1 by sigma 1, y minus mu2 by 2. And minus 2 rho is a multiplication factor. And here uh, we have 1 by 2, 1 minus rho square. So it is a complex expression, but still, uh, if you make a little practice, it will be easier to remember that. So these are the parameters and their ranges are given. Of course, x lies between minus infinity to plus infinity, y minus infinity to plus infinity, mu1 and mu2, and sigma 1, sigma 2 greater than 0. Rho lies between minus 1 and 1. So having specified this joint density function, few observations we will see that if rho equal to 0, rho equal to 0, so we substitute rho equal to 0 means, so this factor will be 0, this will be 0, this will be 0. So ultimately it reduces to 1 by 2 pi sigma 1 sigma 2, because this part rho is 0, and then e to the power minus half, and only these two terms will be left over. This one, uh, this one, and this one. So x minus mu1 by sigma 1 square, y minus mu2 by sigma 2 square. Now, if we separate these terms, so we can write this 1 by sigma 1 root 2 pi e to the power minus half x minus mu1 by sigma 1 square into another factor which is coming 1 by root 2 pi sigma 2 e to the power minus half. So this is normal. This is normal. So basically what we have got? We have got the product or product of the two marginals. One which is one is represented by x and another is for y. So this is the density function of uh, x and this is the density function of y. Okay. So x. So what is the result? Result is that if we can write the joint density function as the product of marginal. Okay. So this is the joint density function when rho equal to 0, which we have factored into two parts, one for the marginal of x, another for marginal of y. So it shows that when rho equal to 0, x and y are independent random variables. Now, in general, this result is not true. We have seen earlier while uh, discussing the joint distribution of any two random variable. So there we have seen that if rho equal to 0 or rho equal to 0 implies the covariance equal to 0, it does not imply that x and y are independent. But in particular the bivariate normal case, if rho equal to 0, then it implies x and y are independent random variables. So here that's why I have written, in case of the bivariate normal, if rho equal to 0, it implies that x and y are independent random variables. However, in general, this result is not true that we have seen earlier. So this is one of the observation we have made from the joint density function of the bivariate normal distribution. Now, the next question arises, how to get the marginal of x and marginal of y. Means we want to find the density function of random variable x, density function of y from this given joint density function. So we know the result that if the joint density function is known, we can if fxy is there, then if we integrate with respect to y, we get the marginal of x. Okay, so here we are integrating with respect to y. So of course the derivation is little lengthy, but again I have explained you. Say we write the joint density function and integrate over minus infinity to plus infinity with respect to y. Okay, so here it is. Anyway, anyway, so this we are integrating with respect to, maybe I make it smaller. So it is dy. Okay, we are integrating with respect to y. So here we are putting dy. Now, so in order to simplify this integration, that we make use of method, use of the substitution. Substitution means here we make substitution of y minus mu2 by sigma 2 h equal to u. Okay, so dy will become sigma 2 du, and the h as y varies from minus infinity, u will also vary minus infinity, y varies to plus infinity, then u take. So the above integral reduces to this form. So 1 by 2 sigma 1 sigma 2 under root 1 minus rho square is already there. This quantity we have just borrowed it here. Okay, and this quantity, because we are integrating with respect to y, so the terms which involves x, we can take it out. So this term, this particular term has been taken out. So here we have multiplication of minus 1 by 2 under root minus 1 by 2 1 minus rho square x minus mu 1 by sigma 1 square. Having taken it out, our integral reduces to minus infinity to plus infinity exponential, and this term will be there, minus 2 1 minus rho square, and this will become, because this we have substituted u, so it is minus 2 rho x minus mu 1 by sigma 1 into u, and this is u square. So this particular is u square, and then dy equal to sigma 2 du. So here we have put sigma 2 du. So having done that, now this particular integral we have to simplify. So as you can see, there is a square term here and there is a product term. Okay, so we make it a perfect square. In order to make perfect square, we add rho square x minus mu 1 x minus mu 1 by sigma 1 square and subtract the same quantity. So one quantity we have, same quantity we have added, same we have subtracted. So ultimately this one is taken out. So this, once you take it out, so this will become rho square with a plus sign, 1 by 2 1 minus rho square. So this quantity, and x minus mu 1 by sigma 1 square. So the earlier term which we have carried out earlier, all these terms are here. Okay, and this is the extra term which has been taken out, and then ultimately it becomes e to the power minus, if you combine this term with the plus term, so u minus rho x minus mu 1 by sigma 1 whole square du. Okay, so this term, if you simplify, it reduces to this form, and one sigma 2 get cancelled from here. So here you are left with this term. Okay, now we have to simplify this part only, this integral. So again, this, in order to simplify this integral, we again make a substitution, that inside the bracket term, this bracket term, we put as t. So this also we have taken inside basically. Okay, square root of under root 1 minus rho square. So this is equal to t, and if you simplify, then you will get finally this result. So this is the final result which we have got after the simplification. So from here, as you can see, that the marginal of x fall is normal distribution with mean mu1 and sigma 1 square. Similarly, one can derive the results for y, and that will be also normal mu2 sigma 2 square. So from the joint density function of the bivariate normal, the marginal density function of x and y are both normal with respective mean and respective variance. So this is one of the results. Now, since we have to solve the problem, that we have to find the conditional result. So condition, in order to get the conditional distribution, we have to put the expression of fxy in the numerator. Okay, we have got the marginal in the denominator, because marginal we have just proved that it is normal. So again we have to simplify this expression. Okay, so this is a very important result, as you will see ultimately after few steps, that what you have to do is that few terms here it will get cancelled, say sigma 1 root 2 pi, sigma 1 root 2 pi. So this from here you simplify, and this term is taken in the numerator. Okay, so whole expression is in this form. Okay, it is minus sign, so in the numerator it goes, it becomes plus this. So after little manipulation, as you can see inside terms, because this particular term is also taken inside this bracket. So x minus mu1 by sigma 1 square rho square minus 2 rho x minus mu1 y minus mu2 plus y minus mu2 by sigma 2 whole square. So again, as you can see, it is a case of this inside bracket we can represent in terms of the perfect square. So x minus mu1 by sigma 1 into rho minus y minus mu2 by sigma 2 rho square. So this this bracket has been simplified here. So simplified means you take the sigma 1 sigma 2 and then x minus mu1 rho times sigma 2 y minus mu2 sigma 2r. So this is the expression we have got. The constant term still we are keeping. Okay, so that will go continuously. So this term we can further simplify, and we can rearrange the term, and you will see that this sigma this term is there, e to the power minus 2 1 minus rho square sigma 1 square sigma 2 square. Then this you have x minus mu1 rho times sigma 2 y minus mu2 sigma 1. So what we have done now, that we have taken sigma 1 square common. Okay, so means here we have sigma 1 square. So x minus mu1 rho sigma 2 by sigma 1 y minus mu2 sigma 1 square we are taking common, so it becomes square, and then here you have to adjust. So ultimately, as you can see, 1 sigma 1 square get cancelled from here. So this term and this term get cancelled. So 1 by sigma 2 square, and this we can write into this form: y minus the term in the bracket mu2 plus rho sigma 2 by sigma 1 x minus mu1. Okay, so final result of the conditional density function of y given x turns out to be in this form. So as you can see that the constant term we have carried out throughout from very beginning. So this is 1 by sigma 2 root 2 pi under root 1 minus rho square, and this term. Now I make a little simplification that this particular term, okay, I just represent by mu dash, and square root of this particular term I say sigma dash square. Okay, so this quantity, as you can see, square root of this quantity is appearing here, sigma 2 under root 1 minus rho square. So which is sigma dash root 2 pi is there, e to the power minus 1 by 2 sigma dash square, because this quantity we have assumed sigma, this is sigma dash square. Okay, so sigma dash square and y minus mu dash square. So this particular is density function is normal, okay, with mean mu dash and variance sigma dash square. So what we have got is that y given x, because we are finding the conditional density function of y given x. So the conditional density function of y given x is normal with mean mu dash and variance sigma dash square. So this is an important result. And what is mu dash? As you can see, it is Mu dash is the mean of this quantity. What is mu dash? Mu dash always represent the mean of the quantity under consideration. So quantity under consideration is the conditional random variable y given x equal to. So mean of this is mu dash. So mu dash is expected value of y given x equal to x, which is mu2 plus rho sigma 2 by sigma 1 x minus mu 1. And similarly, sigma dash square is the variance of this particular quantity, which is sigma 2 square 1 minus rho square. So this is the mean, this is the variance. So finally, if you write this result in terms of the notational form, then you will see that the conditional distribution of y given x is normal with mean mu2 plus rho sigma 2 by sigma 1 x minus mu 1 and variance sigma 2 square 1 minus rho square. Now, as you will see that it is a complex expression because this is the main result which will be used. Okay, so how to remember that? Okay, so how to remember is that first of all you are dealing with y and conditioned on x. So the first term will be mu2. Okay, it is related to this plus rho sigma 2 by sigma 1, y sigma 2 by sigma 1 if you consider y by x. So standard deviation of y and standard deviation of x. So y by x is sigma 2 by sigma 1, x minus mu 1. Okay, so conditioned variable is x, so x minus mu 1, and variance will be simply the sigma 2 square, whatever the variable is coming here, y. So variance of y is sigma 2 square, and 1 minus rho square will be the multiplication factor. So on this basis, if I have to write what is the distribution of x given y, because many times we have to find the probability in form of the x given y. Okay, so instead of going through all the derivation, one can go through all the derivation. So x by y will have normal. Okay, so since x is coming, so mu1 rho sigma 1 by sigma 2 x over y, so sigma 1 over sigma 2 y minus mu2, and the variance will be sigma 1 square, means whatever the variable is here, into 1 minus rho square. Okay, so these are the two main results which you have to remember, or you have to look for solving the problem. So let us go back to the problem. What was the problem? That in the class test 1, if some student has scored 80 marks, what is the probability that he will be scoring greater than 80 marks in class test 2? So we have established that conditional density function of y given x, okay, is normal. So if it is normal, we need to find out this quantity and this quantity. So since all the informations are given, if you look at the problem, it's mu2 is 83, rho is given 0.8, sigma 1 by sigma 2 4 by 5, x minus mu1, x is 80. Here it has been specified, okay, because this is the conditioned value of x. So here conditioned value of x is 80 and mu1 was 75. So mean we have got 86.20. Okay. Similarly, variance of x, variance of y given x is sigma 2 square into 1 minus rho square. Okay. So this variance does not depend upon this x value. Okay. It is only sigma 2 square 1 minus x square. Whereas the mean depends upon this 80. If you change this, then correspondingly this value will change. So 16 1 minus 0.8 square 5.76. So if you remember the theory which we have already discussed in the case of the normal distribution, that if a certain random variable is normally distributed with given mean and variance, we can always find the probabilities using the required probabilities using the standard normal table. So it has been established now that y given x is normal, okay, with mean 86.2, variance 5.76. Then this probability we can convert into the standard normal. So standard normal is that 80 minus 86.20 square root of 5.76. So probability z greater than minus 2.58, and this value you can see from the table. So it is 1 minus 0.0049, which is 0.55. So this is how the problem is solved if the if the x and y are bivariate normal distribution. So is it clear? Bolo bhai, is it clear?
Yes, sir.
Okay, so basically in any of the numerical problem, you have to remember these two results. Okay, what is the conditional distribution of y given x, x given y, and sometimes you can remember the forms also. So another problem I am going to show you that here the joint density function is given. Okay, this form is given to you. Okay, and mm, mm, uh, the form is basically the expression of bivariate normal density function. Okay, so we need to find what is the probability this one. Okay, so this is the question. This is given. Okay, given. So given the joint density function, that bivariate normal, and you need to find out this. Okay, so first of all, you are not given what is the mean of x, what is the mean of y, what is the variance of x, what is the variance of y, what is the correlation coefficient. So all these information you have to extract from the given bivariate normal density function. Okay, so you have to match this particular expression with the standard bivariate normal density function. So as you can see, we have the expression x minus mu1 by sigma 1 square. So mu1 is 5. Okay, sigma 1 is 1 from here. Okay, now y minus mu2. So mu2 is 10. Here mu2 is 10. Sigma 1 square, sorry, sigma 2 is 5. So sigma 2 is 5. So sigma 2 square is 5. Here it is sigma 2. Okay. So x minus mu1 by sigma 1, y minus mu2 by sigma 2. So we have got this. Now we have to find the value of rho. So how do we get the rho? So what you do, this is the constant. Yeah. Okay. So this constant term, if you remember that we have standard form 1 by 2 pi sigma 1 sigma 2 under root 1 minus rho square equal to 6. Okay. So I have equated. Okay, this is the standard form and this is the given form. Okay, which is taken from here. So now if we simplify this, you will get 1 minus rho square is 9 by 25. And so from here you get two values of rho. One is plus minus two values of rho plus minus 4 by 5. Now we have to choose the among these two values. Okay, whether it should be plus 4 by 5, it should be minus 4 by. So basically you go back here. What is the standard form? We have minus 2 rho. Okay. x minus mu1 by sigma 1, y minus mu2 by sigma 2. Okay, so if it is negative, if rho is negative, it will become plus. So since here minus sign is appearing, so basically rho has to be positive. So rho is 4 by 5. Is that clear? Why we are taking? Because we have to, everything we have to put into the standard form. Okay. So in the standard bivariate normal density function, this term involves minus 2 rho x minus mu1 by sigma 1, y minus mu2 by sigma. Okay. So basically x minus mu1 by sigma 1, so 1, y minus mu2 by sigma 2 is 5. So basically here it is minus 2 rho will come. So from there you can get 4 by 5 also. Otherwise you can get it here. Only minus and plus will be decided from here. Because here you see this is the standard form. Okay. So minus 2 x minus 5 by sigma 1, y minus mu2 by sigma 2, so 1 5, so 4 by 5 is left minus 2. So directly also you can get 4 by 5 from here instead of going through this place. So anyway, ultimately you have to get the parameter. So we have got this parameter rho. Okay, so once we have got rho, so we have to find this probability. Okay, so we need to find out the conditional mean, conditional variance. Y given x. Remember that. If it is x given y, then you have to use the another other formula. So y given x mean, okay, x equal to 5. Here it has been specified. So basically we have to find expected value of y given x equal to 5. So mu2 rho sigma 2 by sigma 1. Why I am writing? See, unless you write many times, you won't be able to remember. Because nowadays you are appearing in the online examination and all those things, and you have the access of notes and books, etc. So, but otherwise in the other examination which is conducted uh, under invigilation, you have to remember this. So to remember that, as I told you, there is a trick that y and this corresponds, then the ratio corresponds sigma 2 by sigma 1, rho will be multiplied. So anyway, so you have calculated conditional mean and conditional variance. So y given x is normal with mean 10, variance 9. So now we can easily calculate this one. So since the conditional uh, distribution is known, it is normal with mean 10, variance 9. So we use the usual property that we convert into the standard normal variate. So 13 minus 10 divided by 3, this will become z. 16 minus 10 by 3, so 1 z less than 2, 5 2 minus 5 1. So that you can see from value from the table, and you will get the required probability. So this is uh, this is how the problem is solved when the joint density function is given, and when the parameters are given, then required probability you have to calculate. So some problems are given in the assignment sheet, and you need to work out the some problem. Is it fine? Any question if you have? Hello? Hello? Anybody is there?
Yes.
So is it fine? Have you followed this bivariate normal?
Yes.
हम्म कोई डाउट नहीं, सब ठीक है? So if everything is fine, then we move to another topic. Okay, so I'm closing this. So now another topic is, so this is the last topic. Okay, is it visible? Is it visible?
Yes, sir.
Yes. Okay, so basically it is a topic related to the transformation of the random variable. Of course, uh, we have seen in the case of the univariate case at our single random variable, say x is PDF or PMF is given, then we know how to find the PMF and PDF of some function of x, and we did some examples: y is equal to 2x plus 8, y equal to mod x, y is equal to x square. Any sort of function you can consider and you can find out, and there is a result which has been stated in the form of the theorem. If it is monotonic, means either increasing and decreasing, there are results, and if it is uh, increasing, decreasing, or in the whole domain, the function changes its behavior. So in that case, we have another result. So now consider two random variables, x1 and x2. So their joint PMF or PDF is given. So once the PDF or PMF is given, we can define functions of, say, y1 equal to g1 x1 x2 one function, y2 is g2 x1 x2 another function, y3 another function. Means we ultimately we have defined a function of x1 and x2. Okay, here it is one function, here is another function. So the function could be of any form, say x1 plus x2, it is a function of x1 x2, x1 minus x2, it is a function of x1 x2, y1 is x1 over x1 plus x2, y1 is x1 over x2, or y2 is x1 x2, y2 is x1 plus x2. So y1 is e to the power x1, y2 equal to x2. So in many application, we need to find the PMF, probability mass function of y1 or y2, or we may need to find out the joint density function of y1 and y2. So problem is to find out the joint PMF or PDF, because once you have the joint PMF, you can always find out the marginals. Say for example, if the joint density function of y1 and y2 is known, we can find out the marginal of y1. Means suppose our objective is to find out the y1 equal to x1 or x1 plus x2. So how to get it? To get, in order to get the density function of y1, we define another random variable y2. It is your choice. Okay. Say for example, I have defined x1 plus x2. So in that case, I can find the joint density function of y1 and y2, and once we have the joint density function of y1 and y2, we can integrate over y2 and we can get the density function of y1. So let us first consider a simple case. Usually the problems become simpler in the case of joint probability mass function. So here uh, consider the two discrete random variable. X1 is the number of defective item produced by machine 1. X2 is the number of defective item produced by machine 2, and their joint probability mass function is given. Okay, say x1 takes these are just artificial data. So but it satisfies the condition of the joint probability. So x1 takes value 0 1 2 3, x2 takes value 0 1 2 3, and p00 p01, all these entries represent the joint probabilities, and the corresponding marginal are known. So now if I define a new random variable y1 as a function of x1 and x2, and suppose we have considered 2x1 plus x2, so this is my g x1 x2, this is my g x1 x2. Okay, so this is the function. So now I have to find out what is the probability mass function of y1. Okay, so first thing is that with the values the random variable x1 and x2 takes, x1 takes 0 1 2 3, x2 takes 0 1 2 3, we can compute the values taken by the random variable y1. So x1 0, x2 0, it is 0, x x1 0, then x2 can take one value. So here all the values have been listed for y1, which is 0 1 2 3 up to 9. Okay. Now we need to calculate what is the probability y1 equal to 0, because once we have got the value of y, we need to find out their respective probability. So y1 0. So y1 0 means when you look back here, y1 will be 0 when x1 is 0 and x2 is 0. So x1 0, x2 0, and x1 0, x2 0, this probability 0 0.02, 0.02. Now y1 1, if we have to find, so when y1 will be 1 when x1 is 0 and x2 is 1. So x1 0, x2 1, 0.06, x1 0, x2 1, x1 0, x2 1 is 0.06. y1 2, now y1 2 will be when x2 equal to 0 and x1 equal to 1. x1 equal to 1, x2 0, or x1 0, x2 takes value 2. So these 1 0 and 0 2. So this probability is 0.13. Okay. Similarly, y1 3, as you can see, you can calculate, and all the other values you can easily calculate. So in the case of the joint probability mass function, things are little simpler. You have to just find the value of the new random variable, and corresponding probabilities can be calculated by looking back the joint probability mass function of x1 and so now the next case comes the continuous random variable. So in continuous random variable, we are given the joint density function, and we will be given the function, and from there we have to find out the joint density function of y1, y2, and ultimately we have to get the marginals of y1 and y2. So we will discuss tomorrow. This is the last topic, and we will try to finish so that after the class test we can start the stochastic process. So we'll see.
Sir, in the above page,
Hello.
in the above page, that is the marginal of y1, no, sir?
Marginal of y. Yeah, means you need to find the some function of x1 and x2. So our our problem is that if y1 say x1 x2 is given, we need to find what is the probability mass function of y1, okay, or y2, or sometimes we need to find out the joint probability mass function of y1 and y2. So again the things becomes complex little bit. Okay,
So
so
probability mass function of y1 means nothing but marginal of y1.
क्या चीज
A PMF of y1 And marginal of y1, both are same.
Same. Whenever we discuss the joint concept, because here you are dealing with only two random variables, but sometimes we have to deal with the 2, 3, 4 or n random variables. So the concept of the marginal, when we talk about the marginal, means it is a one particular random.
Thank you.
Okay. So we will meet tomorrow.